Dear students, today we will discuss the heat of reaction varies with temperature. This relation is given by Kirchoff. In today's lecture, we will derive the Kirchoff equation. Before going to the Kirchoff equation, we have to study some terms. The first term is molar heat capacities. Suppose we have a substance which quantity is the 1 mole and you heated that substance. After some time, its temperature is increases by 1 degree unit. During this increase, the substance gain some kind of heat. That heat is called as the molar heat capacities. Therefore, molar heat capacity can be defined as the heat change where change in 1 degree in temperature at constant pressure. It is called as the molar heat capacity at a constant pressure. At constant pressure, we can denote molar heat capacity as a Cp, and at constant volume you can denote the molar heat capacity as a Cv. It can be given as the formula Q upon T2 minus T1, Q upon T2 minus T1. Okay, Q is your change in heat during 1 degree temperature increases. Okay, that is total we obtain like that way. Now we have performing a reaction. Our starting material is A gives the B by two different ways. That is, A gives the B at T1 temperature and T1 temperature, the same temperature, and again this B absorb energy and it is having temperature T2. Then second route, A at T1 temperature gives the B product and temperature is this absorb the energy and temperature becomes T2. In this case, temperature is the T2. First route is like that, and second route from A to B is shown like that. Okay. Now, during conversion of A to B, the heat, change in heat is given as delta H1. And during this process, change in heat is given as the delta H2. Okay, heat is evolved during this process is given by delta H1 at temperature T1, and heat is evolved during this is the delta H2 at temperature T2. The molar heat capacity for a product is considered as CPB. CPB means what? The molar heat capacity. P stands for the at constant pressure and V is for the product. The molar heat capacity for our product is a CPB. Okay, and molar heat capacity for reactant is CPA. Now, during the first process at temperature T1, your product is converted and at the same temperature. During this temperature, heat is evolved is given by delta H1. And second process, our product is heated to the temperature T2. Therefore, total heat absorbed during this process by the product is given by its molar heat capacity of product T2 minus T1. This gives the heat absorbed by the product during the first path. This value we obtained previously. We discussed what is the molar heat capacity. In this case, we have discussed that our molar heat capacity Cp is given by Q upon T2 minus T1. Therefore, heat is given by Q is equal to Cp T2 minus T1. Therefore, for reactant Cpa, Q is absorbed is given by Cpa T2 minus T1. Okay, this is, we have cleared that point here. The heat is absorbed by the product is Cpb T2 minus T1. Now, during this second path, the temperature was at T1. During this process, A2, your reactant A2A at temperature, we heated the reactant to the temperature T2. Okay, then we evolved the energy. During this heating, your temperature of reactant will be T2, and heat absorbed by the reactant is given by Cpa into T2 minus T1. Okay, and then heat is evolved, but there is no change in temperature takes place. Remember that. Okay, during the first path, at the first step, the heat is evolved. Okay, that is first step. Step first for root first, for heat is evolved, but temperature is T1, no change in temperature T1. Okay, heat and temperature are different concepts. Remember that. In first step, heat is evolved at temperature T1, and that particular heat is given by delta H1, change in heat, that is heat is evolved. And during the second route, this is our first route. During the first route, at second step, heat is absorbed by the product, and absorbing heat, its temperature will be increases to T2, and this absorbed heat is given by the formula Cpb, that is molar heat capacity of product into the change in temperature. Okay, that is, it is also called as the, for total process T2 minus T1 is also given by the delta T. Okay, therefore second step, heat is absorbed by the product is given as Cpb, that is molar heat capacity of product into change in temperature T2 minus T1, that is delta T. This is about the first process. Okay, then total change in heat we can given as total change in heat for first process is given as delta H1 plus Cpb into T2 minus T1. Okay, total heat is change we given as delta H1 plus Cpb T2 minus T1. Now, by considering root second, If you consider root second, in first step for root second, this is the first step. During the first step, heat is absorbed. Okay, then temperature T1 is okay, product is absorbed, temperature T change T1 to the T2. That absorbed heat by product, that is B, is given as Cp, by the reactant. You change it by reactant. In this case we have product, reactant is Cpa into T2 minus T1. This is for the heat absorbed or heat change of reactant is equal to Cpa into T2 minus T1. Okay, in first route heat was first heat is evolved. Okay, in first route here is heat is evolved and heat is absorbed. In first route, in second route, heat is absorbed. First step, heat is absorbed, and in second step, heat is evolved. Okay, remember this difference here. Now, first step is completed. Then heat is evolved by the reactant and it gives the product at temperature T2. Okay, temperature of A is the T2 and temperature of B is the T2. During this process, heat is evolved is given as delta H2. Therefore, total change in heat is given as, for the second route, total change in heat is equal to delta H2 plus Cpa T2 minus T1. This is the total change in heat during the route second. Now, we have a rule, that is law of conservation of energy. We can use here. Okay, the change in energy or change in heat in first step is equal to change in heat in second step, because we obtain the same product by different routes. Therefore, change in heat at the first route becomes equal to change in heat at second route. Now, by comparing this becomes equal to this by using the law of mass action, law of energy conservation. We have the change in heat in a route first is equal to change in heat in route second. Okay, by putting the values you will obtain here change in heat route first is equal to delta H1 plus Cpb T2 minus T1 is equal to delta H2 plus Cpb T2 minus T1. Now, by rearranging the equations, delta H1 will be goes to the right hand side, then is equal to, and this will came to the left hand side. For this there is delta Cpa. Therefore, delta H2 minus delta H1 is equal to CPB T2 minus T1 minus, okay, this positive becomes negative in this side, CPA T2 minus T1. Okay, that CPB is your average molar heat capacity of the product and CPA is the average molar heat capacity of the reactant. Therefore, delta H2 minus delta H1 is equal to, this common term will take outside the bracket, T2 minus T1 CPB minus CPA. Therefore, this T1 we will move towards the left hand side. Then delta H2 minus delta H1 upon T2 minus T1 is equal to CPB minus CPA. Okay, we will now delta H2 minus delta H1 upon T2 minus T1 is equal to delta CP. This is total change in molar heat capacity at constant pressure of a reaction. Okay, CPB minus, okay, therefore average molar heat capacity of a product minus CPA is the average molar heat capacity of the reactant, is nothing but the change in molar heat capacity of a particular reaction. Therefore, this is given by delta is the change in CP for a reaction. Okay, this is a change in heat, molar heat capacity at a constant pressure for a reaction is given by this type of our equation. Now, for a constant at a constant volume, how is the equation can be derived? Suppose we have at constant volume, we have a equation that is delta H. We have equation that is the delta H is equal to delta U plus P delta V. We have the one of the equation. Now, when our volume is a constant, then V2 minus V1, both quantities are constant. Therefore, V2 minus V1 is equal to 0. Therefore, delta H is equal to nothing but the delta U. The delta U is the change in internal energy. U stands for the internal energy, and delta U is the change in internal energy. Now, by putting this delta H in this equation, we obtain delta CV. Okay, that is the molar heat change in molar heat capacity of a reaction at constant volume is given by delta CV is equal to delta U2 minus delta U1 upon T2 minus T1. In this case, delta CV is nothing but CVB minus CVA. Okay, CVB is the molar heat capacity, okay, average or mean molar heat capacity of the product at V means the at a constant volume minus that quantity CVA is the quantity average or mean molar heat capacity of a reactant at a constant volume. Okay, this term is the like that we can explain. This delta U1 U2 is the change in internal energy at a temperature T2 and change u delta u1 is the change in internal energy at a temperature T1, or we can say like that, that is at temperature T1 delta u2 and temperature T1 at delta u1. This is the way we have derived the Kirchoff equation. I hope you understood this concept and how to derive the Kirchoff equation. Thank you very much.